Problem is, it's not continuous. So, but continuity, the formal definition of continuity tells me that, well, what does it tell me? Alex, can I get a green marker? What does the formal definition of continuity tell me? It tells me that no matter how close I would like to be to you, there's some interval around C such that all the points will land there. And so now I'm going to use that definition and I am going to say, well, I'm going to set epsilon to be the gap in between f of C and u. So there is some gap here as it's drawn on our picture that we're trying to show is impossible. And the contradiction is going to come from setting epsilon to be that gap. Because the definition of continuity tells me that I can get, no matter how close you want me to be, I'll be there. Well, now I want you to be that close. Okay, so that backboard is the thinking board. This is just the tediously doing it board. What I'm going to do is I'm going to set epsilon to be u minus f of c. And since f of c is less than u, of course, that implies that u minus f of c is positive. So this is indeed a candidate for epsilon, because this is supposed to be true for any epsilon greater than 0. Okay, so if that's the case, then what I know is by the definition of continuity at x equals c, there exists some delta. Let's call it delta. And what's true about that delta? Well, it must be true that if the difference between, if I'm within delta of c, then the difference between f of x and f of c has a difference of epsilon. Or I'm within epsilon of that. That's what continuity tells me. Okay, well, cool. Now, let's suppose that I am pretty close to C. Okay, so suppose that that this is true. So suppose that I'm pretty close to C. Suppose that I'm within delta of C. Let's explore what comes from that. Well, if that's true, then here's what I know. I know this. And again, not thinking, just tediously doing it all out. This tells me that, this tells me like this, right? It's just arithmetic. And of course, what is epsilon? By definition, it's like u minus f of c, right? So now I have that f of x minus f of c, and this time I'm going to only choose the right-hand side because that's all I need for this proof. So if the definition of epsilon is u minus f of c, then I'm just going to stick that in right there. And what I've proven is that f of x is less than u. Okay. So, conclusion, if I am, now I'm going to write it in sort of people terms. If x is between c minus delta and c plus delta, then f of x is less than u. Proved from the definition of continuity. And that's exactly what I did over here, right? I picked this delta, c plus delta, c minus delta. I picked this delta, and then I said, yo, if you are within this interval, then it must be, I guess I only proved half of it, right? I don't know. Right, Marcus, this is fine? I think this is fine. Yeah. Yeah, if I'm in here, it must be, it must be the case that, that the output lands below u. But there's the problem, right? The problem is that I now have points which are to the right of C, which are less than u, and that's my contradiction. So in particular, can you think of a particular point which would produce this contradiction? C plus 1/2 delta. Brian Myers says, take C plus 1/2 delta, for example. C plus delta over 2. Is C plus delta over 2 within delta of C? It certainly is, right? And what I proved from C plus delta being pretty close to X, delta close, or pretty close to C, what I now know is then what I just showed here is that f of C plus delta over 2 has to be less than u. Why is that a problem? Yeah, in particular, if C plus delta over 2 is less than u, what do I know about that number C plus delta over 2? It's in S, right? Then, by the definition of S, if when I plug this number into F and I get something less than u, then C plus delta over 2 is an element of S. But if it's an element of S, then C cannot be an upper bound. Oh wait, what am I trying to say? Yeah, if this is an element of S, then C, this is a contradiction with the fact that C is supposed to be the largest number, which is bigger than all the elements of S. Contradiction because C is an upper bound. It has to be, hold on, I feel like I'm messing something up. No, we go right here, right? It's in particular, it's this line. Again, you don't have to be smart, you just have to follow the quantifiers, so you have to be really smart. Right? This is the definition of what it means to be an upper bound. And now what am I really doing is, I'm sticking in C plus delta over 2 in for X here in the definition of upper bound, the definition of C being an upper bound. If C plus delta over 2 is in S, which it is, then C plus delta over 2 has to be less than or equal to C, and it isn't. There's exactly the contradiction. It's by plugging C plus delta over 2 in for X in this definition of what it means for C to be an upper bound. Contradiction! Case 2, go faster. I'm actually going as fast as I can. I find this hard.
Back for a moment.
What's up?
Getting it so like at least that's on camera for a second.
Oh, yeah, that's a good idea.
Okay. They can pause the video.
It's been half an hour? Yeah, good. Well, how long did I say this would take?
5 to 10, then like.
Oh, no, that's fine. I don't think I gave an hour. I would have said 20.
You said 15.
I said 20. Yeah, half an hour, 20. That's a long time. Okay, case 2. Case 2 is associated with that other picture. Case 2 is that, but now we'll go faster. Case 2 is that f of C is greater than u. Okay, what am I going to do now? Yes. Now set epsilon to be the difference in the other way, right? F of C minus u. Exactly. Now the contradiction is going to come from, again, if you look back at that picture, over here, this was the case when f of C was greater than u. Now the problem becomes, now I'm going to set this gap to be epsilon. Again, this picture is not continuous, and the problem is we're going to have our points which are in S, which are less than C, which is going to be the problem. Okay. So, and now, also this gives you some kind of sense of actually why Cauchy and Weierstrass use this definition. This is something we actually don't do in analysis 1A, is sort of use the definition of limit to like prove theorems, right? We only prove limits, but this is sort of a case in which you seem, okay, whatever. I'll shut up and just do it, because that's the point. Good. Epsilon be f of C minus u, so now by definition of continuity, what's true again? So just by definition of continuity at x equals c. There exists a delta, call it delta. And what is true about this delta is this. Same as before. And now, suppose then that, so suppose that, again, we're on this interval. Okay. Then, what is true? This is true.
You want an inequality?
Okay. Well, okay. So we have now f of x minus f of c being for sure between negative epsilon and epsilon. Now it's only the left side that I want, I guess, right? The opposite of epsilon is u minus f of c. So I steal the left half of that compound inequality, and this proves that in fact u is less than f of x. Okay. So what we conclude again is that if x lies somewhere between c minus delta and c plus delta, then I have just proven that f of x is bigger than u. Why is that a problem? Oh, by the way, also over here, the assumption is that x can't be c, right? So I'll put a little x is not c, because my assumption was that x is somewhere in between c minus delta and c plus delta, but not c itself. Okay, what's the problem with f of x being bigger than u? Yeah, now we have, oh, I lost my green, but now we have some interval c plus delta, c minus delta around c, and now it must be on the, it's on the left side now, right? Somewhere in here, here is now the problem, is that somewhere there are points here which land above u. And so any one of those points would be, in fact, can I just use c minus delta itself? No. I think I have to do the same delta over 2 thing, right? Yeah, so take, yeah, and so now take c minus delta over 2 again. C minus delta over 2 is between c minus delta and c plus delta. So f of c minus delta over 2 is greater than u. Why is that a problem? Yeah. Exactly. This is now another upper bound, right? Because if that number is bigger than u, and S is the set of all numbers which land in there that are less than u, then by definition of upper bound, it must be the case that c minus delta over 2 is an upper bound. And c minus delta over 2 is less than c. This contradicts the fact that c, contradiction with fact that c is the least upper bound. Because I found an upper bound which is in fact less than. Analysis. This is analysis. Good, because you have a class called analysis on your transcript. You have 2 of them, so you should probably learn some analysis before you graduate. All right. How do you feel about this? This was all just an excuse to just like rub your nose in like what 19th century math has become. Ben Phelps, what do you think?
It's very nice, actually.
Oh, you like it? Yeah. Who else likes it? Who hates it? Who has strong feelings somewhere? You hate it? You don't like it because it's just like hard and boring? Yeah, pros and cons. Sage, give me a pro or a con.
A con is just this like epsilon delta boost.
So con is it's like hard, is what you're saying.
Nah,
Can I get something better than hard?
It's like there are too many like quantifiers.
Wait, hold on, Sage is talking MIDI.
Never mind.
Sage says never mind. People watching at home, Sage says never mind. Ben Felber.
It's very verbose. It's not as like immediately obvious. You sort of have to think of everything rather than just being able to like see it with the same graphical immediacy.
Yeah. Yeah, and by the way, jerks who write math textbooks, they only do this. They never do that stuff over there, which is that kind. Well, actually, some good ones do, but sorry for math professors. Yeah.
Well, like I get it, why they don't do that, because that seems really arbitrary. Like that's my con. Is it because it's
Right.
kind of arbitrary? Because you
In
don't
particular,
have,
how do I know to like do this, for
yeah,
example?
exactly.
Right.
You don't know f of c is u technically, so you're just like, we're gonna make this weird inequality to like pretend that it is to show that it isn't, but it is. It's kind of,
Oh, I thought they didn't do the pictures because like it's just easier to type that up than it is to like draw it.
I think they don't do the pictures because, well, okay, I'll add my commentary at the end. What's good about this? Yeah.
It's almost easier because here it's like so obvious that you don't even know what your assumptions are and what you're trying to prove because it's just like duh. But here
Yeah.
if you actually write down like exactly what you know, you can get to what you're trying to prove.
Yeah, ooh, I like that. So, yeah, more. I have some things to say, but maybe you'll say them first. Yeah.
Like line to line, like you can, each line just kind of follows.
Oh, he's feeling the rigor. He's feeling, we should get class t-shirts made called Feel the Rigor.
Yes.
Someone do that. I'll definitely buy one. Yeah, he's feeling the rigor, right? He and Yael are basically saying, ooh, I like this because I now know that no one's gonna like trick me, right? I can just go through line by freaking line very carefully with like a microscope and check every little tiny fact to make sure it all comes together. That's kind of what you're saying, right?
I didn't say I liked it.
Yeah, you didn't say like it, but he said that's a pro. So someone else can do that. There's a pro. Yeah. Yeah, that's good, right? It should be good for your proof. It's a good thing if your proof is like checkable by other people. Yeah. Other things, pros, cons. We haven't got any cons yet, except for it's annoying. What?
I feel like it's the main issue.
That's the only con? What about the fact that it's yeah?
Well, it's based on
I mean,
this, like the,
Sage. Ooh, Sage has something to say.
it's based on the epsilon delta like concept, which is already like complex enough. Like people like argue that like it was kind of weird that you pick like quantifiers. It was like a weird definition that we talked about before, where like how we
Yeah.
define the limit to be like epsilon, like this weird epsilon delta statement that we just accepted as true. And it was like you have to
Yeah.
base on that.
Yeah, this is another one of those days where supposedly what I'm hopefully trying to get out of you is like some deeper understanding of what math is or what math isn't. What the hell is math? Do you feel like you understand the intermediate value theorem better? That's a good question.
yes.
Yeah?
Well,
I like this
I
vague
believe
concept
it
that
better.
points in there
I trust it
between.
more
No.
She trusts it more. Why do you trust it more?
because I mean it's just a solid proof.
It's a solid proof. What does this proof depend on?
Leads you wrong.
What does this proof, what, okay, so Victoria has more confidence now in the intermediate value theorem. I should have done some interviews like before and after, asking you when you were in calculus, how sure you were about the intermediate value theorem, and then saving the recordings for later to
That made sense to me a lot. Like this slope is just that just made sense to me.
Yeah, the intermediate value theorem.
Yeah.
No one doubts that, ever, like, no one doubts that. But you are already 100% sure. Victoria was 100% sure when she was a sophomore and learned this. Now she's more than 100% sure. Okay, yeah.
But like we were 100% sure because we think that these things are intuitive, like about
Right.
real numbers.
Yeah.
So if you're doing like in some non-intuitive math system, I don't know the words, but like
Yeah, it's called math.
you wouldn't just be able to say it's intuitively for sure if you started with different axioms. So like when we did it, I didn't know what we were basing the intermediate value theorem on. It was just like
Yeah.
right.
I mean, yeah, this is just totally intuitively clear. I'm pretty much with Winnie. I feel like I understood this fully and completely. My confidence in this could not have been higher. It just makes complete and total sense. I guess Do I understand the intermediate value theorem better now? I don't know. What I do understand better now is the dependence of the intermediate value theorem on the least upper bound axiom. So I guess in some ways I'm as confident now in the intermediate value theorem as I am in the least upper bound axiom. So that's the thing, right? But this is the axiomatic method, right? You never get full confidence. You just get confidence in certain results pending acceptance of the least upper bound axiom, which is, do you have more or less confidence? That's another question. What's your level of confidence of the least upper bound axiom?
95%.
Yeah, same as 5%. You say less than that. Exactly. Oh, something good educational thing just happened. Hannah, I have less, and so do at least two other people, I'll pretend that's all of you, less confidence in this extremely abstract and obscure axiom that I've gotten through my whole life without knowing up until this point. It didn't seem to bother me at all, than I did in the result. And yet the entire point of the axiomatic method is I'm supposed to, the extreme confidence, at least is the Euclidean version, the extreme confidence in the basic axioms, which we know by intuition, are then going to sort of bleed out into the wonderful world of theorems, and now I'll be as confident in theorems as I am in the axioms. Now what we have in the 19th century is this march towards patching things up and therefore going backwards, and coming up with extremely abstract and obscure axioms that are not only not obvious, but no one had even thought of them as being even propositions before. And we're supposed to accept this as an axiom, and I'm supposed to get the confidence in my intermediate value theorem is supposed to flow from my confidence in this axiom. Seems all backwards, right? Okay, good, yeah.
Why didn't they just like make the intermediate value theorem into an axiom?
Yeah, I mean, they had kind of been doing something almost like that, but then you would also need an axiom for like the extreme value theorem. You would also need an axiom for the bounded convergence theorem. You'd also need an axiom for the Bolzano-Weierstrass theorem. So it was sort of, and this is how the axiomatic method works. You keep going backward and backward and backward, and if you can prove all of those things from this one thing, then it appears that this is the guy that's actually doing all the work. So maybe he should be the axiom. Yeah.
Can you prove the least upper bound axiom from the intermediate value? Can't you?
I don't know. Maybe. Okay. All right. Good. All right. So this was the. All right. So hopefully, we've accomplished several things today. One, we proved the intermediate value theorem. Go home and tell your parents about that. We got a little taste of what analysis is like. Two, we kind of had can you imagine yourselves in the position of 19th century mathematicians who've been doing calculus the normal way, and suddenly Weierstrass says, no, this is calculus. What's not on this board, what's not in this proof is no intuition. No intuition was required. You could have absolutely no idea what the hell was going on, and you could just be checking this proof line by line. I could give this to some freshmen in functions who understood quantifier logic and didn't know calculus. There is no such person. And he could check to see that this proof was correct, even if he had no idea what the hell was going on. Right? All you need is, actually, let's make the full list of what you need. What do you need? You don't need intuition. What do you need?
You need to understand inequalities.
You need to understand inequalities. Actually, this is an important conversation. Everyone's watching at home. What are all the things that you do need? Let's list all the things, not just mathematical, philosophical, and you can mention pencil and paper if you want. Let's list every single thing that you need to accept this proof. You need to understand inequalities, he says. Good, I wasn't even going to say that, but that's very good.
You need to understand
You need to understand arithmetic.
the characters used.
You need to understand, so logic. You need to know logic, right? Looming behind all of this is some formal logic which enables you to make all these inferences. By the way, that did not exist yet at the time of Weierstrass, so that's interesting. So you need logic, quite a lot of logic actually, multiple, triple quantifiers. You need to understand inequalities, you need to know arithmetic.
Proof by contradiction.
Functions, proof by contradiction, yeah. So if you already understand proof by contradiction, if you already understand certain properties of inequalities, in particular, I use the fact that if f of c is not less than u and f of c is not greater than u, how do I do? Then f of c must be u, right? So I use the sort of so-called trichotomy property of, did I? Yeah. Something like that. Yeah. So for any two numbers, you're either less than or greater than or you're equal to it. And if it's not less than or greater to, then it must be equal. So I use various, so suddenly in our march, what?
Also set theory.
Set theory is involved, yeah. Sets, I need to understand sets, I need to understand logic, I need to understand quantifiers, I need to understand less than symbols, I need to understand. Okay, if you accept all those things, then we have rigorously proven this, right? This is the goal, this is what math has become. Rigor means no intuition. Get all that intuition off the page, just do it with rigor. Okay, so, and guess what's gonna happen next? If you're as obsessed with rigor as Weierstrass is and other people in the 19th century, what's your next move? You're gonna demand axioms for all those things you just mentioned. Arithmetic, less than symbols, set theory, right? We can't just let these things just linger. We can't just assume that we understand set theory like it's no big thing. And that's basically what we're gonna be doing for the next 3 or 4 weeks is attacking with more of this quest for rigor, axioms for arithmetic, axioms for the less than symbols, axioms for set theory. This is what happened. Sorry, Sage. Good. Primaris, how much value would be
Immeasurable value.
can you give a 5-minute sketch of the extreme value theorem, or do you want to just do your whole thing all over again?
We only have like, we could.
Do you want to do like 2 more slides or something, 2, 3 more slides, or what do you want to do?
We had one theorem that we rushed through, and then the actual extreme values that we really do it all.
Okay.